All right, Dr. Clark back again, and in this video we're going to learn about line integrals that involve vector fields. So this is going to be really interesting, and just pay attention and you'll see how vector fields can interact with line integrals. A little bit of background first is there's these sort of four types of curves. The best is this, what we call this simple closed curve here. A simple closed curve is just a simple loop that closes up and it doesn't intersect itself. So a not simple closed curve would be down here. See how it intersects itself? That makes it not a simple curve, but it does loop around back to itself, so it is closed. A simple would be this one here. It doesn't intersect itself, but it's also not closed up. And then this one here would be not simple and not closed. It intersects itself and it doesn't close itself back up. So there's going to be some technical theorems that talk about whether a curve is simple and closed, and so most of the time we'll want a curve to be for sure simple and ideally simple and closed. All right, so up until now these examples have been extending what we knew about our arc length, and then saying, well, we could talk about the mass of a wire or, temperature of a wire or something like that. But what we're going to do now is factor in vector fields. So imagine you have a spaceship and it flies through the Earth's gravitational field. There would be an effect of the Earth's gravitational field on that spaceship. Essentially, the Earth would do work on the spaceship, pulling it towards the Earth. And so we could actually add up the cumulative effect of that gravity field on the spaceship. Or if you're riding your bike home and you're pushing against the wind. Well, we could add up how much work you do pushing against the wind the entire time you ride your bike or something like that. So there's a vector field of wind or gravity or something. That vector field or electromagnetic field, right? That's going to do work on an object, and we can calculate exactly how much work is done on that object using calculus. Okay? The way this works is it's called a line integral over a vector field. So I want you to look right here. This integral over a curve ds, that's a line integral. And there's a function. So when you think integral of a function, ds, with respect to the length of a curve, that is a line integral. And what's going on is in place of the function, we are putting f dot t. It's a dot product of two vector fields. But if you dot product two vectors, you get a number. So really, we're just integrating up some quantity. It just turns out that quantity comes from a vector field. And the way you want to imagine that is, let's say you're on some curve here. Well, the tangent vector would tell me what direction you're going along the curve. And maybe there's wind that's blowing you at the same time as you go along this path. Well, if the wind is, say, the vector field F, then when you dot product F with T, well, if the wind is blowing with you, when you do that dot product, you'll get a positive number. So you'll get a positive contribution. But if you're going this way and the wind is blowing this way, then when you dot product it, you could get 0 if the wind isn't pushing you at all. Or if the wind is pushing, maybe the wind's blowing this way and you're going this way, then you could get a negative dot product. So what this is doing is it's adding up all the contributions of the vector field in the direction of travel. Okay? And then it multiplies by the length and adds them up over the entire path. Okay? So let's read the full thing now that we kind of have seen the idea. F is a continuous vector field on a region. C is a smooth curve. T is the unit tangent vector to the curve. The line integral of the vector field over the curve is equal to this integral over C f dot t ds. Okay? And how does this work with a parameterization? Well, if you had a parameterization r of t, then if you took the derivative, r prime of t, that would give you the velocity. Okay? Now the velocity is in the same direction as t. T and v, the tangent vector and the velocity, would point in the same direction, but t would have length 1 and v could be considerably longer if you were going fast. So what ends up happening here, if I can maybe just erase some of this stuff here to get a little bit of space going here, what you want to imagine is what we would normally have is t would be the velocity vector divided by the length of the velocity vector, right? That's what the tangent vector is. And ds is the length of the velocity vector dt. So what happens when you get t and ds next to each other? Well, you would end up with r prime over the length of r prime times the length of r prime times dt. Well, you can actually cancel these out. And so what sometimes happens is they will write this as f dotted with r and then dt. Because t is one unit length and ds has length built in. Well, r has length built in and dt is just dt. So you can sort of package these two things up together this way. I missed the derivative, r prime. Okay, and it's from this sort of cancellation right here. R prime dt is the same as t as a vector ds, and r prime would be a vector as well. Okay, so that's what you're going to see when you write down. So this would be the definition here, but this is how you end up actually computing it because your curve is going to be given by some parameterization. So this is how you compute it, and this is technically what it is. If the vector field PQR is given, then you can sort of take P, Q, and R, dot product it with x prime, y prime, z prime, and then you get P, x prime, Q, y prime, R, z prime. That's just doing the dot product of the vector field and the derivative of the position. Okay? One thing the textbook does if you're reading in the book is I prefer this here. This is what we just explained, but the book will write this as dr. I think that's a mistake, but I don't write the textbook, so I don't get to do that. So you will only see me use this notation, but if you do look in the book, they're going to say dr. All right, so that's what a line integral is of a vector field. It's really the same thing, right? It's the same thing that we've had before, but we're using a vector field as the function we want to integrate, the height of the fence or whatever. Okay? And then work, the idea of work, when we were saying the wind is blowing against you, that's generating work. Well, if the wind is that vector field, then this line integral is equal to work. So work is just the name for what this line integral actually gives you when you do this problem. Okay? When you work in the tangential direction. Okay, so that's what work is. It's just an integral of a vector field, dotted with the tangent vector with regards to arc length. Okay. There's another idea, which is circulation, where we... Yeah, well, actually circulation, that's the same thing as work. It's just another name for work, because if you imagine, why do they call it circulation? So imagine you've got like a vector field that's kind of like circulating around or whatever, and you go up in a path in a circle. Well, the tangent vector would be that way, and if it was circulating, you would sort of get work. So circulation is really just another name for work, but it's what we use when you have a closed curve. Okay, so to have circulation, we have to have a closed curve. Work does not require a closed curve because you could have a path and the wind could blow you along a path. But to talk about circulation, we just want it to be a closed curve. That's the main idea there. Okay, so that's one upgraded idea to our line integrals, the idea of work or circulation, which is what if a vector field pushes you in the tangential direction. But you might start to wonder, well, what about the normal direction? What happens if we want to talk about our path, but we want to know not if the wind is blowing us along the path, but what if the wind is blowing us off the path, right? Instead of thinking of the tangential direction, thinking of the normal direction. Well, we call that flux. So flux is essentially the amount the wind blows you to try to tip over your bike. You know, if you're biking this way, then work tells you how much the wind pushes you, and flux tells you how much the wind tried to tip you over, kind of a thing, coming at you across or push you off your path, kind of a deal. Mathematically, all we're going to do is replace the tangent vector with the normal vector. Everything else is exactly the same. And we're going to do this in 2 dimensions here. So let F be some vector field, okay? And R is my path. And time from A to B, simple closed curve. The flux of the vector field across the closed curve is F dotted with the normal vector ds. And then you might wonder, well, how do you actually compute it? Because when we had tangential vector, we could take the derivative. Well, now we need the normal vector. Well, what's going to happen here is the tangential vector is always given by x prime, y prime, right? That's a tangent vector, or at least the direction. You'd have to divide by the length to get the unit tangent vector. We want the normal vector, so we want something orthogonal to that, and it turns out that y prime comma negative x prime is orthogonal to x prime y prime, and if you do the dot product, you'll get 0. You'll see why that's the case. So at least in a plane, you just take your vector field and you dot it with y prime comma negative x prime. That's your normal vector, okay? And this is not a unit normal vector, but it's the same thing where the normal vector ds is equivalent to this y prime comma negative x prime dt. The length is packaged up in here in the dt, whereas here the length is packaged up in the ds, and this is unit length. So we kind of, it's that same kind of a trade, okay? And if the curve is parameterized counterclockwise, then we use the outward normal vector, then we get the outward flux. So we tend to want to parameterize these curves counterclockwise. So keep an eye out for that when you're doing these problems. All right, and in the next video, we'll do some example problems of how to compute flux and circulation. So stay tuned for the next one, and we'll do some examples.